Hi, good morning everyone. This is Jagdish, Assistant Professor of ECE, SNS College of Technology, Coimbatore. Today, in our optical and microwave video lecture series, we are going to discuss about the topic optical fiber and devices. Come, let's get into the topic. Optical window. In astronomy, the optical window is the optical portion of the electromagnetic spectrum that passes through the atmosphere all the way to the ground. Most EM wavelengths are blocked by the atmosphere, so this is like a window that lets through only a narrow selection of the what is out there. Though the sun is particularly active in the positive wavelength, it is called optical because the wavelength we can see are in the range. The window runs from around 300 nanometer ultraviolet B and the short end to the range they use roughly 400 to 700 nanometer and continues up through the visual infrared to around 1100 nanometer, which is the near infrared range. There are also infrared and radio waves that transmit some infrared and radio waves. The radio waves runs from the about 1 centimeter uh, to about 11 meter. In medical physics, the optical window is the portion of visible and infrared spectrum where living tissue absorbs relatively little light. This window runs approximately from 650 to 1200 nanometer. At shorter wavelength, light is shortly absorbed by hemoglobin in blood, while at a longer wavelength, water strongly absorbs infrared light. In optics, it means usually at least mechanically flat, sometimes optically flat, depending on the resolution requirement. Piece of transparent for wavelength range of interest, not necessarily for visible light. Optical material that allows light into optical. A window is usually parallel and is likely to be anti-reflection coated, at least if it is designed for visible light. An optical window may be built into a piece of equipment such as vacuum chamber to allow optical instruments to view inside that equipment. For UV, VAS spectroscopy, these types of window are usually made from glass or fused silica. In IR spectroscopy, there is a wide range of materials from barium fluoride, germanium, zinc, selenide, and sapphire that transmit light into far infrared. These windows are either built into circular or rectangular configuration. Lambda equal to attenuation dispersion, lambda equal to 10 by L log P in by P out. So it is expressed as that is dB by kilometer, L equal to fiber length caused by absorption, scattering, and bending. So intrinsic absorption by glass material itself due to the absorption band in ultraviolet region, energy level transition, tail of the curves enter the operation region, small as compared to IR absorption. EN loss inversely proportional to wavelength, typically 0.1 dB per kilometer at 1200 nanometer. Follows empirical relation as Arbon's rules, that is E photon energy. So lambda UV equal to C e power C e power E by E naught. That is C and E naught are empirical constants. So signal degradation, that is absorption, intrinsic absorption by glass material itself, crystal lattice vibration in infrared region. In frequency lies within resonant frequency of vibration. Tail of curves enter the operation region. Typically 0.1 dB per kilometer at 1500 nanometer. So attenuation, dispersion, scattering, microscopic variations in material density. Glass is randomly connected network of molecules having higher or lower than average density. Compositional fluctuation of SiO2, GeO2, and P2O5 give refractive index fluctuations. In fluctuation, distance very small with respect to wavelength causes rayleigh type scattering of light. It is photons moving in all directions. Effective signal strength gradually reduces proportional to lambda hyphen 4 reduces with increases in wavelength. So MI is scattering when RA fluctuation distance comparably to wavelength can be reduced by reducing imperfections during manufacture. Carefully controlled, carefully controlled exertion and coating, increasing fiber guidance by increasing delta. So thank you. So we have what we have discussed here is the optical fiber communication. So now the assessment question is you have to find out the answer. I mean, you have to explain the real-time optical fiber communication where we are applying and the process how it is working. That you have to explain group wise. Thank you.